Welcome back, students. We are about to embark on unit number 5 of this course, and this is the topic of gases. Don't forget that on your textbooks, this unit might not correspond exactly to chapter 5, so it depends on which edition of the book you have. Let's talk first of all about some of the general physical characteristics of gases. Most of these you can gather from your own personal experiences, right? Gases assume the volume and the shape of their containers. They're the most compressible state of matter. They will mix evenly and completely when confined to the same container. In other words, a mixture of gases will have pretty much no limitations as to how many gases, how much of it you can put in a container. And they typically have much lower densities than liquids and definitely of solids. And you can see the pictures here of gas molecules. These would be nitrogen and oxygen mostly, and you can see the space between them. We will essentially look at the molecular level of gases in the third part of this unit. You should be able to remember that several elements we discussed back in chapters 2 and 3 exist in nature in the form of diatomic molecules, and they are gases: hydrogen, nitrogen, oxygen, fluorine, and chlorine. Also add to that the noble gases, and you have the collection of elements that exist as gases at room temperature, about 25 degrees Celsius, and 1 atmosphere. We'll discuss what that means in a moment. Here is a table that shows these elements and other ones like ozone, for example, and then some compounds. A very limited sample here, but just to get you an idea that there are many compounds that also exist in the form of gases in nature. Now, we're going to talk about some properties of gases, and the first one we're going to focus on is pressure. The physical definition of pressure is force divided by the area. And you can see the difference when you hammer a nail. Let's say that the hammer is coming down with equal force in both scenarios. Notice that in the example on the left, that force is exerted over the very small area of the tip of the nail, whereas on the right, it is being exerted over the broader area of the head of the nail. So because the bottom part of that fraction is smaller in the left side, that means the pressure is greater. So just remember the relationship between force and area. Now, just like a ball exerts a force when you bounce it against the wall, gaseous atoms or molecules also exert a force when they collide with a surface. So in a sample of gas, the result of all of these molecular collisions is what we end up measuring as pressure. Technically, pressure then would be the force exerted per unit area by the gas molecules as they strike the surfaces around them, particularly in the container. Now, if we were to define the units of pressure based on this definition, we would get units of newtons, which is force, divided by square meters, which is area, and a newton per square meter is called a pascal. It's not a very wieldy unit to work with in our case in chemistry. So in the 17th century, Evangelista Torricelli came up with a different way of measuring pressure. He took a tube that had a column of mercury in it, and he inverted it over a container that had also mercury in it, and realized that the mercury column would drop only up to a certain level. It didn't spill all the way out. And what he figured was that the atmosphere was pressuring the mercury on the outside and thus preventing the column of mercury inside the tube from spilling out. He measured the height of that column and came up with at sea level, the column was 760 millimeters. And so based on this, we've built a scale where we measure the pressure not on the basis of the physical units, right, of what we call the Newton meters, the pascals, but rather, much like we do with temperature, we'll just measure the kind of like the size or the height of a column inside the thermometer. In here, we call this a barometer, and we say that at sea level, we have a column of mercury of 760 millimeters. And we call each one of those millimeters a torr. So this would be 760 torr. And we can also build the unit called the atmosphere. So 1 atmosphere would be the pressure of air at sea level, which would cause a mercury column to sit at exactly 760 millimeters of mercury. If we want to convert between pascals and atmospheres, here is the conversion. And of course, in our American society, we don't use these units anyway, right? If you feel you're tired, you're going to look at units of pounds per square inch, or PSIs. And when you hear the weather report, they talk about the atmospheric pressure in inches of mercury. So here are the conversions for those. In your end of the chapter problems, your homework, you may have some practice problems converting between these, but we're going to skip that, and pretty much all we'll need to know is how to convert between atmospheres and torr slash millimeters of mercury. All right. Okay, now remember the molecular model that we're talking about. We're saying that pressure is generated by the collisions of the gas particles with the walls of the container. So, based on everyday observations, what are some ways in which we can increase the pressure of air? For example, you have a flat tire, what do? You pump air in. In other words, you can increase the amount of air until you get the desired pressure, right? Another example, this is a hot air balloon. When you heat the air inside the sleeve of the balloon, you essentially get pressure inside, right? So it's obvious that increasing the temperature of air will also increase the pressure. Now here's an interesting one. This lady is lying down on an exercise ball, and what prevents her body from collapsing all the way down to the floor? Well, as the volume inside the ball is compressed, right, the pressure increases until it equalizes the pressure that her body is being exerted on by gravity, right? So decreasing the volume of air, in other words, compressing air, also increases the pressure. We know some of these things from experience again. We know that the air around us exerts a certain pressure. We said that at sea level, that pressure, we're calling it 1 atmosphere of pressure. However, if we took that same surface area and extended it up in the atmosphere, like a column of air, and we measure what is the pressure at 4 miles high. Well, at that point, the pressure drops to about half an atmosphere. And if we were to go to 10 miles, the pressure would drop to 0.2 atmospheres. Of course, that's because we have thinner air, less air, lower pressure, right? Now, these are qualitative observations, and of course, scientists would like to turn these into quantitative relationships. So, Robert Boyle conducted a series of experiments in which he studied the relationship between the pressure and the volume of a gas. And you can see the apparatus there on the left. This is a J tube. Essentially, you have a J-shaped tube with a column of mercury in there that has trapped a bubble of a gas. And of course, you can try this with different gases: nitrogen, oxygen, carbon dioxide, helium. And then what you do is you add mercury so that you can cause a compression of the gas, right? And what we're going to say is that the height difference between the two sides of the column of mercury is going to be the pressure that's exerted by the bubble of gas inside the left part of the J tube. So the experience was that, for example, in case number A, at 100 milliliters of gas, you had essentially equal pressure. But at 50 milliliters, in other words, when you compress the gas, you created a column that was 760 millimeters of mercury. And at 33 milliliters, you had a pressure of 1,520 millimeters of mercury. In other words, as the amount of mercury increased, in other words, as the pressure of the mercury of the gas increased, the volume decreased. So you increase the pressure on that gas, you decrease the volume. Now let's make this into a graph. Let's plot the volume against the pressure. And as you can see, like we saw, as the pressure increases, the volume decreases. But this is a curve and therefore not very wieldy for analysis. So what Robert Boyle did was he decided, well, let's do this. since it's obvious that they are inversely related, let's plot the volume against the reciprocal of the pressure. And voila, you get a straight line. See, a straight line is very easy to analyze because, as we saw in our graphing exercise, a straight line on a graph has an equation and it makes values predictable. So here's what we're saying. We're saying that the volume is inversely related. If you're not familiar with this symbol here represents a proportion, right? So it says that the volume is inversely proportional to the pressure. In other words, it's related to the reciprocal of the pressure. So that means that the volume multiplied times the pressure always gives you a constant. At any point on this graph, the pressure times volume product should be a constant. Or in other words, P1 times V1, in other words, the pressure times the volume at one point, equals P2 times V2, pressure times volume at another point. Now, very careful. For this to work, we had to keep the temperature constant, and we had to make sure there's no leakage or of gas. We had to keep the amount of gas constant, because remember, we already discussed that temperature and the amount of gas can also affect the pressure. We want to isolate the relationship between pressure and volume here. And this is what we call Boyle's law. Now, believe it or not, you experience Boyle's law with every breath you take. If you've taken any biology courses, you remember that in our chest we have a muscle called the diaphragm. When the diaphragm contracts, what it does is it goes from a curved form into a straight form, which means that it opens up the cavity in your chest. It increases the volume and therefore decreases the pressure in your lungs. And because the pressure inside your lungs decreases with respect to the pressure on the outside, the air from the outside moves in. Now, when the diaphragm relaxes, what happens is, you can see on the right there, the lung volume decreases. That means that now the pressure in the lungs increases, and that pushes the air out. Of course, there's also the physiological component here where, the air you inhale, you absorb oxygen from it, and the air you exhale has extra carbon dioxide in it, but that's more for physiology than it is for chemistry here. So we're interested in Boyle's law. Let's do a little exercise here. Let's say I have a sample of chlorine gas and it occupies a volume of 946 milliliters at a pressure of 726 millimeters of mercury. What is the pressure of the gas in millimeters of mercury if the volume is reduced at a constant temperature to 154 milliliters? Okay, let's write out Boyle's law. Says that the pressure times volume product should be a constant. In other words, P1 times V1 equals P2 times V2. So one of the key things here is to identify, which one is which, who is P1, who is V1. Okay, we're starting at a pressure of 726 millimeters of mercury, so that's P1, and a volume of 946 milliliters, so that's V1. We're going to arrive at a final volume of 154 milliliters, and the question is, what will be the pressure at that point? That is P2. So again, make sure you identify correctly which value goes with which variable. So since our unknown is P2, let's take Boyle's law and let's rearrange it and solve for P2, right? And now we can plug in the numbers for P1, V1, and V2. No need to make conversions of units at this point, because as you can see, when you plug in the numbers for P1, for V1, and for V2, the milliliters are going to cancel out, and you're going to end up in units of millimeters of mercury, which is your goal. Now, remember, qualitatively, Boyle's law says that the pressure and volume vary inversely to each other. So if I decreased the volume, what should I expect to happen to the pressure? That's right. If one decreases, the other one should increase. So I should arrive at a value of pressure here that is higher than my initial pressure. And that's going to check my result. Here's my result. Does that make sense? Well, it makes sense in the sense that the pressure at the end is higher than it was at the beginning. So at least it moved in the correct direction. Whether I made a math error or punched the wrong numbers in my calculator, that's a different issue. But the point is, I want to make sure that my result makes sense. Okay? Cool. Let's look now at the relationship of the volume and the temperature. In this experiment, we have a capillary tube with a gas that is trapped by a drop of mercury. I notice that as I increase the temperature, the gas expands. In other words, as T temperature increases, V, the volume, increases. This tells me that there is a direct relationship between the temperature and the volume. So, in experiments done by Jacques Charles, they quantified this relationship, and you can see here the graph generated when you plot the volume in liters against the temperature. And what they did here was all these experiments are done at constant pressure, and each line represents a different amount of gas in each one. Notice that for each one of them, you have a straight line. Just as predicted, the volume is directly related to the temperature. As the temperature increases, the volume increases, and notice that the increase is linear. Now, one interesting thing here is that if you extrapolate all these lines back to a quote-unquote zero volume, they all intersect at the same temperature. In Celsius, that temperature would be negative 273.15 Celsius. This temperature is called absolute zero. Now, technically, we cannot measure these temperatures experimentally because all gases are going to condense into liquids before they even reach that temperature. So that's why we extrapolate these lines. So in 1848, William Thomson, aka Lord Kelvin, proposed a scale where he said, let's use this scale based on this absolute zero, and let's build a scale where all the temperatures are positives, and this temperature scale is called the absolute temperature scale, or sometimes in honor of Lord Kelvin, it's also called the Kelvin scale. Notice that in this scale, the temperature at which water freezes would be 273.15 Kelvin, and the temperature at which water boils would be 773.15 Kelvin. Notice that we don't say Kelvin degrees, just simply Kelvin. So let's restate Charles's law for the relationship between volume and temperature. It says that the volume is directly proportional to the temperature. In other words, the volume is going to be always some constant times the temperature. Another way of writing this is for 2 points on that graph, V1 over T1 equals V2 over T2. Now, because temperature is in the denominator of these ratios, it cannot be zero. Also, it cannot be a negative number because that would generate something absurd, which would be negative volumes. So that means that we must always express temperatures when we work with these gas laws in Kelvin. And to find that, we take the temperature in Celsius and we add 273.15. Now, the final value will be rounded according to how many decimal places the Celsius temperature was given in. All right? Cool. So let's do a little sample exercise here. Let's say a sample of carbon monoxide gas occupies 3.20 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? Okay, so let's write out our expression of Charles's law, V1 over T1 equals V2 over T2. Now remember, temperatures here cannot be expressed in Celsius. We had to convert them into Kelvin. So let's go ahead and express 125 degrees Celsius in Kelvin. We add 273.15. And because the given temperature didn't have any decimals, we have to, round off the decimals in the final result. So it's 398 Kelvin. Now it's a matter of deciding who is V1 and who is V2. Well, V1 is 3.20 liters. T1 is 398 Kelvin. V2, the final volume, is 1.54. And T2, our final temperature, is our unknown. Once more, let's rearrange Charles's law to solve for T2. Be careful when you move these variables around. We sometimes get lost when we're doing fractions. Be V2 times T1 divided by V1. Again, since I am decreasing the volume, what should happen to the temperature? That's correct. Since the volume is decreasing and the temperature is directly related to it, the temperature should also decrease. So T2 should be smaller than T1. So I'm going to put the numbers in now. I'm going to cancel out the liters units. I'm going to end up in Kelvin, and the resulting number should be smaller than 398, and the result is 192 Kelvin. So at least as far as which direction the temperature moved in, we are in the right direction here. I'll give you a few seconds to work that out. You can try the calculation, see if you get the same result. Okay, let's look at a third expression of the relationship between properties in gases. This is Avogadro's law, and this is a plot of the volume against the number of moles of gas. In other words, the amount of gas. And what we find is that as we increase the amount of gas at a constant temperature and pressure, so does the volume. So the volume is directly proportional to the number of moles, and by convention, we're going to use the letter N to represent the numbers of moles. So that means that the volume is always going to be the number of moles N times some kind of constant, or in other words, V1 over N1 equals V2 over N2, because that ratio is always going to be a constant. Don't forget, in order for this to work, we have to keep both the temperature and the pressure constant, because remember, those two other factors also affect the behavior of the gas. Okay, so we now have three different expressions for the relationships of two properties at a time of gases. Let's see if we can combine them into one general equation. We're going to call it the ideal gas equation. Okay, so Boyle's law said that the volume is inversely proportional to the pressure, of course, at constant moles and temperature. Charles's law said that the volume is directly related to the temperature at constant moles and pressure. And Avogadro's law said that the volume is directly related to the number of moles at constant pressure and temperature. So if we were to combine all three of these, we would say that essentially the volume is proportional to N times T over P. This expression of proportionality can be turned into an equation by saying that volume equals a constant times NT over P. We're going to call that constant R, and we're going to call it the ideal gas constant. And then what I'm going to do is I'm going to rearrange this equation into a more familiar form. PV equals nRT. This is the common form in which we express the ideal gas equation. Notice that it relates all four of the properties of gases that we're interested in: the pressure, the volume, the number of moles, and the temperature. So what we need next is we need to calculate what is the value of R. To do that, we're going to set a gas at a set of conditions that we're going to call standard temperature and pressure, or STP. Now, for our purposes, we're going to say that these conditions are 0 degrees Celsius and 1 atmosphere. Now, just so you know, technically, the pressure for STP is really not exactly 1 atmosphere. We're going to use 1 atmosphere for our purpose, because ultimately what's going to happen is this is going to serve just as a point of reference for us. So experimentally, you can measure different gases and find that at 0 degrees Celsius and 1 atmosphere, in other words, at what we're calling STP, 1 mole of an ideal gas occupies 22.414 liters of space. This is an experimental result, okay? So let's go and write again the ideal gas equation, and let's rearrange it for R. R would be PV over NT, and let's plug in these values you found here. So remember, pressure would be 1 atmosphere. This would be, N would be 1 mole. The volume of 1 mole at STP is 22.414 liters. And the temperature, 0 degrees Celsius, we said is 273.15 Kelvin. So this gives us the value of 0.082057 liters times atmospheres per mole per Kelvin. Yes, the units are kind of like a little complicated, but you'll see when you plug the values into the ideal gas equation, they will perfectly all cancel out. Let's close out by doing a little practice here with applying the ideal gas equation. Notice that this equation allows us to relate all 4 of the properties of gases. So let's ask, what is the volume in liters occupied by 49.8 grams of HCl at STP? Be careful, HCl here, we're talking about the compound, which is a gas, not the compound dissolved in water, at which point we call it hydrochloric acid. All right, so let's set this up. Okay, this is our ideal gas equation. And since our goal is to find the volume, let's go ahead and rearrange this for the volume, nRT over P. Now, we need to find the numbers that we have here. What is the temperature? At STP, that's 0 Celsius, which is 273.15 Kelvin. Pressure, by definition, at STP is 1 atmosphere. And by the way, this 1 atmosphere, we're going to consider it exact. So we don't have to worry about sig figs with that one there. Okay, so we need now the value of N, the number of moles. They gave us grams, but you know how to do that, right? So 49.8 grams. HCl, you can calculate it to have a molar mass of 36.46 grams per mole. And that gives us 1.37 moles of gas. Let's plug in all these numbers into the equation there on the left and also put in the value of R that we determined. Now, in most of these applications, the value of R, we're going to limit it to the 4 sig figs, so 0.08206. You don't have to memorize it, but believe me, you will use it so often that you will remember that value. Okay, so these are the values we have, right? Moles, value of R, temperature divided by the pressure. Let's make sure the units cancel out. So we have moles canceling out with moles. Kelvin cancels out with Kelvin. Atmospheres with atmospheres. And the last unit standing is liters. So that's the correct unit. So at least we know that we had the units here in the proper place. And the final result is 30.7 liters. Okay, so that concludes this part of the unit. We have discussed the laws of gases. I am not requiring that you remember the name of each one of those laws, but essentially, as we'll see in the next section, starting from the ideal gas equation, you can actually derive all 3 of these laws and even some that we haven't discussed. So thank you very much. Let's go on to the next section in our lesson.